Hello, my name is Jonas Schmidt. I'm a PhD student at the University of Erlangen. I'm going to present you our work on evolving generalizable multigrid preconditioners with grammar-guided genetic programming. So I will start with a bit of motivation, which basically consists of the question, what is preconditioning and why do we need it? So we are mainly concerned here with solving partial differential equations, or short PDEs, which are quite foundational for many branches of science and engineering. And to illustrate this in a more concrete way, you can see a video here of the SpaceX Falcon 9 rocket launch. And as you can imagine, the complex combustion phenomena which happen in such a rocket are quite complicated. And usually to analyze this behavior and design such a rocket, or even more efficient or better rockets, we need to model them in form of a system of PDEs. So the problem is that since in most cases the general solution of these PDEs is unknown, our only chance is to solve them numerically, which means that we need to discretize these equations on particular grid over the domain that we are interested in, and we obtain a system of linear equations from that. But unfortunately, in most or many real-world applications, this system is highly ill-conditioned, which means that even small perturbations in the input, when we apply this operator A to it, results in large error. So since we are usually using floating point numbers for the computation of these applications, this makes it even worse, because obviously we will always have numerical errors when using floating point numbers. So one way to improve the situation is to apply a so-called preconditioning matrix M. So if we now consider another system where we apply now the inverse of this preconditioning matrix to the right of A and replace X by Y, we actually arrive at a system that is, depending of course on the preconditioning matrix, much easier to solve. But of course this comes at a price, and the price that we have to pay here is that whenever in a solver we need to apply the original operator A, we now need to solve an additional system which consists of this system of equations here, mx equals y, since now our new operator consists of the inverse of m. So since we need to do this, the main requirement to apply preconditioning with an iterative method, so usually we are interested in applying iterative methods since direct methods are usually not applicable due to the large number of unknowns. We now need also a second solver that needs to be really fast for the systems of the form of mx equals y. But fortunately, multigrid methods are perfectly suitable for this job, since if you design a multigrid method in the right way, it is able to solve a linear system with asymptotic complexity of O of n. So this is, theoretically optimal, just because if to get the solution of such a system, you need to touch every unknown at least once, of course. So multigrid methods in general function by reducing the error, an approximate error, on a so-called hierarchy of discretization. So we basically consider the same problem on differently sized grids with a different step size h, and then some parts of the error can be reduced more effectively like this. So multigrid solvers are traditionally designed by choosing the individual components and parameters from a predefined set of choices. So first of all, we can, for instance, apply a certain number of recursive descents, so on each level. So this leads to different cycle types. Usually one considers V cycles, W cycles, and also F cycles, which are not shown here, but we also consider them. And then second, we have different components. So first of all, we usually want to apply a smoothing scheme, which has the purpose of reducing the oscillatory parts of the error. Then we need to restrict the solution on the approximate solution on a certain grid level by applying a restriction operator to obtain an approximation of the same error on coarser grid. And then if we have computed a correction, we can prolongate back this correction to a finer resolution. Finally, we also can apply coarse grid solver when the problem is so small that we can actually solve it directly. So how can we now push the boundaries of these traditional approaches to multigrid solver design? And here our idea is to use the grammar-based preconditioning design approach. So what we do is we treat the task of designing an optimal multigrid preconditioner as a grammar-guided program optimization problem. So if we now consider that we have a grammar which allows us to describe each step that is performed in a multigrid solver, we can also just alternate each step within this method by choosing a different production. So this allows us to discover multigrid methods of structure that have not yet been considered in the literature. So we can actually get methods which have a unique pattern of computations and which cannot just be described by a single parameter, such like in the traditional multigrid cycles. Furthermore, using different productions, we can actually alternate the operator in each step. So we can choose a different smoothing operator in each step. We can choose a different restriction and prolongation operator in each step. So this allows us to basically have unlimited flexibility in multigrid solver design. So how can we do this in particular? So as usual with grammar-guided genetic programming, we can evolve a population of derivation trees based on a context-free grammar, which is briefly shown here. But since now each derivation tree corresponds to a unique multigrid preconditioner, we can also describe the process of getting an actual preconditioner from this grammar derivation tree representation. So first we can transform our derivation tree to a computational graph, which now consists of all the computational patterns in the multigrid preconditioner, which can in the second step then be translated to an algorithmic representation, which finally can be compiled using code generation techniques to parallel C++ code, which we can then run on an actual problem to evaluate each preconditioner or even solve a real-world application. So to now obtain, based on this approach, optimal preconditioners, we consider or we propose a multi-objective evolutionary search method. So here first we have to talk about the two objectives. So we consider, since we have an iterative solver that is preconditioned, we want to minimize the number of iterations, which corresponds to the speed of conversions of our iterative method. Since then we have the less iteration we need, the faster we get a solution. Second, if we reduce the execution time per iteration, we can also decrease the overall time required for solving a problem. So we implement our evolutionary search method within the Evo stencils library, which has been already presented in some of our previous papers. So here, the most crucial thing is, first of all, the evolutionary algorithm part is implemented using the DEEP framework. But second, the main problem we needed to solve was to evaluate each solver found within the search. And for this purpose, we employ the Excel stencils framework, which has been specifically designed to generate parallel implementation of multigrid methods. And since the cost of each evaluation is still very high, we parallelize the evaluation and also other parts of the algorithm using MPI so we parallelize it to multiple compute nodes actually. And finally, we have also proposed a generalization procedure that is specifically designed for multigrid methods. and which is based on iterative adaptation of the problem difficulty during evolution. So I don't have time to talk about all the details, but you can just read our paper if you're interested into them. So I now want to present our benchmark problem here. So what we consider here as to evaluate our approach is the indefinite Helmholtz equation, for which you can see a formulation here. So this equation is actually quite simple. So it just is the Poisson's equation with an additional term minus k squared. But even though this equation is quite simple here, for large values of this wave number k, it becomes highly ill-conditioned. So it's very hard to solve due to the problems that I've described in the introduction. And therefore, it's actually considered an outstandingly difficult problem for numerical solvers, which you can also see if you take a look into the literature. For instance, this paper gives a good overview why this problem is hard with and what methods are available for it. So to solve this equation, here we apply a pretty standard iterative solver, so a bi-CG step, and we precondition this with a shifted Laplacian. And then for the resulting system m times y equals x, we apply multigrid method in each step. So now I want to show our experimental setup. So we perform all experiments on the SuperMUC NG cluster, which is right now currently one of the largest supercomputing systems in Europe, actually. And for each experiment, we use 8 nodes with 286 cores. So unfortunately, the high computational costs of each experiment here limit the number of experiments that we can perform. So we only perform 10 to just demonstrate that the method is able to work and have at least some basic evaluation. So within the optimization, we actually we generalize our methods starting from a wave number of 80 until we reach a wave number of 320, which is already quite high. So yeah, you can basically look up all the other details, so I don't have the time for that. And to test the generalizability of each solver that we find within optimization, we consider then 3 wave numbers, where the interesting thing is that the largest wave number here is actually larger than all considered within the optimization. So we can actually test whether our solvers generalize to even larger and more difficult problems. And for comparison, we consider common V, F, and W cycles, where we use optimized relaxation factors and the best possible smoother. So here you can see now the results of our experiments. So first of all, we wanted to see how well our solvers methods perform in terms of solving speed and generalizability. So here in this table, you can see the relative solving time compared to the fastest baseline method, which was the V01 cycle. So it's a V cycle with 0 pre and 1 post smoothing step on each level. And what you can see basically is that, first of all, if we consider the median performance for large wave numbers, so we can see that in the majority of cases, actually the methods that we find are really superior to all reference methods, which is already a quite nice result. Second, even better, so if we consider just the best method, so the single best preconditioner that we find, it's by far superior for all wave numbers compared to the best method, which is already absolutely great result for us. But even better, so in 6 out of 10 experiments, we could even achieve conversions for a larger wave number where basically all the reference methods fail. So you can also see this in this plot. So here we show the 3 best preconditioners from both categories, so evolved and reference methods. And you can see that these 3 for high wave numbers are far superior to all the reference methods, while for small wave numbers, they're still competitive. And in 2 cases there. So in 1 case, they're all, so this was the best method, they always superior. So now what remains is why are we not able to get the same best method in each run? And here we need to look into the Burrito distribution at the end of all 10 experiments. So what you can see here basically are all individuals from the experiments at the end of each run. So the red line shows the combined front of non-dominated individuals. And yeah, unfortunately, so for lower iteration numbers, which requires fast conversions, the spread is much higher. And yeah, this is basically due to the fact that for this case, we need a larger expression since the solver needs more operations, and due to the large search space, it's quite hard to find these solutions consistently, but for larger iteration numbers, it looks much better. So finally, I just want to summarize this. So I've presented a grammar-based evolutionary design method for multigrid preconditioners, so which allows to discover multigrid methods of novel structure, which actually have proven to show superior efficiency and generalizability. However, right now the evaluation is limited due to the high computational demands, so we could not show that the method always works. So for future work, I have to refer to the paper since I don't have much time left. And finally, I also want to thank you for your attention. And if you're interested in our work, please also check out our Humies entry, which actually got accepted for the finals, which I'm really happy about. So thanks and hopefully see you.